Hey everyone, welcome to this DP-900 kind of all up exam cram review session. I actually took the exam Tuesday morning. Just like my AZ-900, I deliberately did not look at what was in the exam. I did kind of no prep for it. I hadn't really touched much around data for 9 months. I wanted to get an idea of exactly what was covered. And then after I took the exam, I kind of went back and kind of looked at what's actually in the exam so I could create this kind of prep session. Now, for me, I had 49 questions and I think you had 60 minutes for the actual answering. It's 90 minutes in total, but you get 60 minutes to actually answer the questions. They are very simple format questions. There's no case studies, there's no labs. It's literally either, hey, here's this small question, pick one, or it's, hey, here's some features, drag the box to what maps, or select all the applicable options. That's really all they are. And you should attempt every question. There's no negative points if you get it wrong. So it's better to have a guess. Often you can kind of look at some and know they're obviously not correct and at least limit down what your possible options might be. So try everything. Most of us are taking them at home right now. Just get a laptop if you can, one screen, nothing else in the room. You have to have a camera to kind of take a picture of you, your ID, and then kind of front, back, sides of the room. Relax. If you take the exam and you fail, you've really lost nothing. Sometimes you win, sometimes you learn. If you take it and you fail, it helps you identify the points you're weak at. I did pass. I got 890 something, but it shows you afterwards, hey, here were your strong areas, here's where you were weak. As you take the exam, if you're not sure, try and keep a mental note in your brain. So afterwards, you can go back and kind of look that thing up to help you improve. So anyway, let's kind of get to it and think about cramming for the exam. So the first point is we are looking at Azure Data Services. When I'm thinking about Azure Data Services, obviously we have Azure. And when we're interacting, that's kind of the Azure Resource Manager. Everything we're doing is via the Azure Resource Manager. And so firstly, if I want to interact with that, well, I can do things like I can use the portal. There's things like PowerShell, there's the CLI, there's REST. But most commonly, if I'm provisioning resources, I can create a JSON template. So this is declarative. I'm going to state what I want the end state to be. Hey, I want this Azure SQL Database. I want this storage account with these attributes. Go and make it so. So if you see questions like, hey, what's the right way to provision resources in Azure in a declarative fashion? If you see any of those kind of declarative, prescriptive, hey, I'm going to use a JSON template. That's the way to actually go and create stuff into Azure. Now with Azure, like most things, there's really two planes. I can think about there's kind of a control plane, also kind of management, and then under that is the actual kind of data plane. Now when I'm doing things with the Azure Resource Manager, what I'm preliminary doing is I'm accessing the control, the management plane. So if we have certain roles as role-based access control, if I have a certain role, so I have role-based access control, this could be, hey, I'm a contributor, I'm a reader, there's lots of kind of options here. All those roles, they're to do with the control, the management plane, what I can do to the resources at the fabric level. Typically, they do not give me access to the data directly. Now, if I have one of those roles, I may be able to go and get a key. I may be able to go and change something, but on its own, it doesn't give me direct access to the data. Now, how I get access to the data does vary by type. Some of them, they might have separate ACLs. Some of them, they may be able to use Azure AD credentials, like with Azure SQL Database. I can give Azure AD users rights to the data from within SQL. Give them select, read, whatever. But it's not an Azure ARM role, it's a separate. It might be there is some kind of key, shared access signature. It might be there's a whole separate kind of user data. So in SQL, I can create local users and give them rights, for example. So if you see questions around, hey, you want to give someone access to read this data, it's probably not going to directly be an Azure Resource Manager permission. It's probably going to be, well, maybe you have to create a local user in a SQL database and give them permission. Maybe it's I need to use this key. But realize you have the control plane and the data plane. Control plane doesn't typically give you access to the data. They are separated out. So if you see something like, hey, I need owner permissions on the resource, it's probably a trap. Look and see what my other options are. Now, as we think about kind of types of service we have in Azure, we often kind of see these ideas around, there's layers of things. So if we think kind of traditional, we always think about, well, there's like compute, there's network, and there's obviously the storage. Those are like the core fabric layers. And then we have a hypervisor sitting on top of that. Now, we then have an operating system. We might have runtimes, we might have middleware. And then we have kind of our app and our data. And why I'm drawing this is, in the cloud, we never worry about those things. The fabric, the hypervisor, we never touch that stuff. However, in an IaaS world, infrastructure as a service, I'm responsible for all of those things. So in an IaaS world, if I pick an IaaS, well, then I'm patching the operating system. I'm worrying about firewall. I'm worrying about antivirus. I'm updating middleware. Now, I say application here. When we say application in this sense, we're really thinking about the business application. That's kind of what we're focusing on. And then in a PaaS world, well, I only care about the top layers. Here, if I was thinking about a database, for example, well, in an IaaS world, if I was installing kind of SQL Server, that means I'm patching SQL Server. I'm installing SQL Server. I'm upgrading SQL Server. I'm installing Postgres or MySQL or MariaDB, whatever that might be. So in an IaaS world, I would be having to, yes, I'm kind of installing, upgrading the database. I'm doing all of those, there's all those operational tasks available to me. So there's work involved. So I'm going to think IaaS, hey, there's lots of things I'm having to maintain. If I go to kind of this PaaS scenario, so let's expand this out for a database, and this could be things like Azure SQL Database. This could be things like Cosmos DB. This could be things like Azure Database. So Azure Database is the open source offerings, and we get kind of Postgres, we get MySQL, and we get MariaDB, which is kind of a fork of MySQL. So in these kind of PaaS models, I am not installing the database. I'm not upgrading the database. I get great things here. So what I kind of get is these are evergreen. I'm constantly getting the latest capabilities. It's going to upgrade for me. I have no OS access. I'm not patching Windows or Linux or upgrading it or what about any of those things. They are done for me. They're going to have native HA, high availability. I may have the option to add replicas in other regions, depending on the exact SKU I pick. I have these massive scale capabilities. I can kind of grow them out to very, very large amounts. There's less to manage because, again, it's PaaS. I'm really just focused on, I'm creating tables mainly, even things like indexing. There's a lot of auto capabilities to help create the indexes for me and tune the database and give recommendations to me. So it's a lot less for me to do. In the IaaS world, well, I'd be installing SQL Server, I'd be patching the operating system. So if you see questions around, hey, I want an installation, I want the minimum amount of maintenance to do, it's going to be a PaaS solution. If you see something like this, hey, you must have access to the operating system, well, then it's going to be an IaaS solution. So realize the difference. Think of the layers. In an IaaS world, I am responsible for the OS and above. That includes installing database software, maintaining, upgrading, backing up. Backup is another good one. Backup is kind of native HA, native backup as well. It's just part of these. And there are things to help me in an IaaS world, but I'm still responsible for doing that stuff. But as soon as I go to the PaaS sort of database as a service offerings, a database is kind of just included for me. All I'm focusing on now is using the database. My app connects to it, but there's huge amounts of functionality just natively built in for me. And that's really kind of a key point of that. Now, one thing I would say, most of these things, I can't pause the compute. Often kind of there's the storage, there's the compute, and we pay for those, mostly independently, although some of them, they are blended. I cannot pause the compute for these. Now, there is a SQL serverless option that does let me pause the compute. Azure Synapse does let me pause the compute. That's kind of the new name for data warehouse that builds a lot of extra functionality. But Azure SQL Database, all of these, I can't pause the compute and stop paying for it. So it's kind of an important point of what I can and can't do. And again, a good example here would be SQL Server installed in the OS. Now, I kind of drew this picture of kind of the access and the data. What about actually getting access to the things? So if you think about, well, there's some data service, there's some storage, actually with all my ones and zeros in it, and there's me at my machine, and I want to get to that data. Now, the exact way that's going to happen is, well, that service will have an IP address. Now, if it's public facing, which for a lot of our data services they will not be, there'd be a certain firewall or certain permission. If it's not public facing, my machine has to be able to get to that network. Now, if this was IaaS, if it was SQL managed instance deploys into my VNet. If it was another type of service using a private endpoint, again, an IP in my network, I have to make sure whatever network I'm on has connectivity to maybe the VNet that is on. So that could be accomplished maybe via a site-to-site VPN. It might be ExpressRoute. So I have to be able to actually get to the IP addresses offering the service. Now, additionally, there's probably going to be a DNS name that actually resolves to that IP address. So I have to be able to resolve the DNS name. Maybe there's kind of a shared DNS. If I see something that says, hey, I've changed the IP address of my service, but I can't get to it. Well, have I updated the DNS record? So I have to be able to get to the DNS and resolve it correctly to get the IP to get to the service. And then, of course, to actually connect to it and get to the data, I have to have rights. This is where ACLs come in, a protection come in. Can I actually get to it? So make sure we think about, depending on the type of service we're doing, do I have permissions to get to it? Can I get, actually from a network perspective, to the IP that's offering the service? If there's a DNS, well, can I resolve it correctly? All of those things have to be in place to actually get to and use the data. Okay, so now how do we store data? So I can kind of think about there's different key types of data we'll often see. And the first one is structured. So with structured, we have a well-defined set of attributes, a schema around our data. And often we kind of talk about, from a database perspective, we'll talk about the relational model. So we can kind of say, hey, relational database. And with a relational database, what we have essentially, if we look at the data, we have rows and columns. And what I can think about, so this could be a table. So that table, often what we're actually going to do is we have a schema. So the schema defines, these are the columns, the attributes of the data, and they're this type, text or date or numeric, whatever that might be. We also typically normalize the data. So we rearrange, move it into different tables based on its type to kind of remove waste, remove duplication. We get it into a very good, strict format. So here we have our records, our rows, and then we have the columns. So we have kind of the columns going this way. So I could have, for example, first name, last name, age, height, ID, all these various attributes of it. And what we'll have is kind of a key. And the key, one of these columns, let's just write key here, this will be unique for each record. So every one of these would have something unique, cannot be duplicated. It uniquely identifies that record. Now, when I think about just a regular relational database, I'm talking about records. So again, rows are going across. That's a particular entity, a particular person. The columns, the attributes are going down. That's some aspect, some piece of data about that particular thing. And what we do is we typically write the data that way. So we actually write this to disk, we write a record. And the record would be per row. So there might be a key, so let's say it's ID 1. It might be first name, last name, age, I'm getting old, height, weight, all these different things. But that is a record. Then there'd be other records for all the various people. So I'm writing that away. That's how I'm storing it. And that's great. If the way I'm interacting with the data is, hey, I want to query on certain things, and I want to kind of see all of the data, well, this makes sense. I read records at a time, but I'm interested in all of that data. So that's good. Writing it record for each row is very logical for me. But there's other use cases. Imagine I had the scenario where actually I'm just operating, let's say, on age. I just want to get the average age, break the ages in, or maybe sales, whatever that is. I'm looking at really just one column at a time. This would be very inefficient because I have to go and get the entire record to get this one attribute I care about. So another common kind of format we'll see is actually Columnar. And it will look the same. I've still got the records and the columns of the data, but how it's written to disk, how it stores the records are different. Because what we're actually going to do is store it as columns. So now a record would maybe be, okay, John, Bob, Fred. There were 3 people. That's a record. Another record would be the ages, 45, 33. 29, etc. So I'm storing the same data, but I'm storing it completely differently. Normally I'm storing it records across. Columnar, I'm storing it columns make up each record. And that's super efficient if all I'm caring about is a particular column at a time. I only have to now read this record and I've got all of the ages. So this column-based storage can be super useful. The common kind of format is Parquet. So this is column storage, and Parquet is a common format to actually store that to disk. So you might see that. So these are highly structured. Both of these are tightly defined schemas. These are the columns we have to have them. And again, we have this unique key that identifies a record. So all of these are kind of structured. Okay. So then we can kind of have, well, semi-structured. So with semi-structured, I can think about a loose or no schema. So there's no kind of strict definition. And very commonly today, we think of JSON. It could be XML, maybe even a CSV could count as this, but it's a lot looser with this. There's still a format for JSON, for XML, but I can kind of pick and choose what attributes I want in there. It's a document. So what we think about these is this is kind of a document type store. Now some solutions, even though I'm just writing a document, this JSON document, it will still go and parse this document, maybe go and index fields, so I can still go and search on particular attributes of the JSON document. Things like Cosmos DB can do this. But fundamentally, there's not a set schema it has to follow. I am just writing a JSON document. I'm writing an XML document. Now, we often still have a key to uniquely identify the records, and we have a can't spell. I'll just go over here. And we have a part. Oh, there we go. Let's just do it again. So I have a key, and I also have a partition key. And why we have a partition key is any resource is finite. I have a finite amount of storage. I have a finite amount of compute that can operate on the storage. So if we have huge amounts of data, I can't just store it as one thing. So what partition keys do is I pick a particular partition key, and that's going to be used to separate my data up into logical partitions. Now I want to pick a good partition key. I want an even distribution. I don't want to pick a partition key that 90% of the data falls between one logical partition and all the rest of it is, I get terrible distribution, which will then affect my performance. Because obviously this logical partition, I have n number of logical partitions, well that will actually be stored in a physical. Now I might have multiple logical partitions to one physical partition, but fundamentally I want a good spread, because behind the scenes I'm going to have blocks of compute which connect to blocks of storage. I'm going to divide up my data. So if I have a partition key like Cosmos DB, pretty much all of these documents, they will actually spread the data out. They shard it. You might hear, when we talk about this distribution, you might hear the term sharding. It's a way to break up the data by some aspect of the data. I'm going to distribute it out. So I pick a certain partition key, maybe it's month of the year. Now even that could be dangerous depending on how I'm using the data, because it's going to be a hot month. The current month, maybe it's all of the work, so that may not be good. I'm just giving an example. If I picked month of the year, I'd end up with 12 logical partitions, and it would distribute it out. So we can shard the data out on that. So pick a good partition key, but these documents, they really leverage that. And then, so that's kind of the semi-structured, then we kind of get unstructured. So unstructured, we often think of a blob, a binary large object. Now there are different types of blob in Azure. I'm going to talk about these in a second, but essentially I can store anything I wanted in here. In a blob, I could have images, I could have video, I could have documents, anything I want, I can kind of store in blob. There's no format, there's no structure whatsoever. It's just, hey, store this thing for me. And what we'll actually see in kind of the data world is sometimes I want a hierarchy. And one of the nice things we have in Azure is kind of that we have this data lake. So we have this Azure Data Lake Storage Gen 2, which actually sits on top. So it uses blob, uses that huge capacity, cheap storage, but it adds a hierarchical namespace to it, Hadoop compatible POSIX ACLs, and now I can store all of these things. It's a good landing zone when I want to just get stuff into the cloud. So if I have unstructured data, probably something like a blob, anything I want, we have these different types. Now there are some others we'll hear about. A actual common one is graph. And graph is all about nodes and edges. So a node is some object. So I could imagine maybe I have a person node type, and that person is John. Then I could, so that is a node. And then I could have another person node type, and that's Bob. And then I could have a edge, a relationship that says works for. I might have a completely different type. Maybe this node type, so it's still a node, but this time it's Office. And maybe it's Dallas. And once again, I can have an edge. So these are edges, these relationships. And maybe this one is works at. And I might have lots of other nodes, lots of people report to Bob. Let's get the right color. And what's great about graph is, as you can see, if I care about the relationships between these different types of objects, I can super quickly say, hey, who works at Dallas? Hey, look, there's edges here. Loads of people work at Dallas. Who reports to Bob? So graph is very powerful when I care about the relationships between objects. So that's graph. So it's important to kind of know, hey, okay, that's what that is. The other one you'll see very commonly is kind of key value. For example, Azure Storage Tables is key value. And as the name really suggests, I can have a key and then n number of kind of name value pairs. So I could have a key, maybe it's ID 01, and I might have, it could be anything you want. It could be first name equals John, age 45, etc. But there's no set values I have to have. It's completely arbitrary. I can write it to the same key value kind of store. Every entry could have different name values. I could lots of these stored. So if I just want to store some data, it's useful for that. Again, Azure Storage Tables does this. Cosmos DB has key value stores as well, so there's lots of options. Another common one, well, not as common, is a time series. So a time series kind of database, as the name suggests, it stores the time and some piece of data. So it's separate from key value, a big line, these are separate things. But if I had data coming in, and all I really cared about was, hey, the time it came in and the piece of data. Think of IoT, all these IoT devices with data streaming in constantly. All I care is getting that sensor value. Well, then a time series database would be fantastic for that. Hey, I just want to capture whatever that current value actually is. Okay, so now let's actually look at some specific examples. So those are the kind of the types we have. What do we have in Azure? So the most basic one, the starting block of most of these is a storage account. So an Azure storage account I create in a certain region, and it has various attributes and certain types of data it actually supports. For example, it supports blob. Remember that unstructured data. And I can do block. I can do page. Page is very good for kind of random access in the blob. Manage disks behind the scenes, use page blob. I can have append. Hey, I just want to keep writing to the end of this blob. Imagine it's some kind of log. And as I talked about before, ADLS Gen 2 actually sits on top of blob, but adds an additional API, that hierarchical namespace, etc. We also have tables. So remember, with tables is that kind of key value store. So that's native to the storage account. This would be kind of unstructured. So we have those native capabilities there. We have queue type. So this is where I'm just storing messages. Simply kind of a first in, first out. Something comes in, something reads from it. And then I have files. So files is provided me an SMB 2.1 or 3 file share. So that's an important thing to kind of understand. If you saw a question, it's like, hey, I want to stand up a file share in Azure. What should I use? Azure Files. Hey, I have a file share. I want to move this capability to Azure. I need a cheap, quick to set up key value store in Azure. I want to store unstructured data. So we have all these native capabilities. Now, there are some changes coming. There are some new things. I don't think the exam will bring these up, but NFS 4.1 is coming to Azure Files. It will be a different share type. I create shares under the file. Also under blob, we're going to have NFS 3. So NFS 3 up here for just very large sequential interactions. NFS 4.1 for more random state locking interactions here. So we're going to, all these different types, we get in our storage account. Now remember, let's think about our storage account for a second. We deploy it to a particular region. Azure has lots of regions. Regions are defined by this kind of 2 millisecond latency envelope. There are always 3 copies of the data. I don't see that. I just write my data. Behind the scenes, it makes sure there's always 3 copies. Now, there are some configurations I can do, and it's important to understand these. I do have kind of a redundancy. I can do extra things. So locally redundant storage, LRS. I have those 3 copies in a particular data center within the region. I can do ZRS. So those 3 copies over 3 AZs. So what does that mean? So if I think about, just for a second, if I draw a region, so that's a region. Again, it's that 2 millisecond latency envelope. Well, the region is actually made up of multiple data centers. And when they're exposed, they're called AZs, kind of AZ1, AZ2, and AZ3. If I do locally redundant storage, all 3 copies of that data is in the same data center. If I do ZRS, zone redundant, those 3 copies are spread over 3 different AZs within the region. So it's still within the region, but now I can survive the blast radius of a data center going down. So if you saw a question, it was like, hey, I want to store my data within a region, but I need to be able to keep access even if a particular data center sees a failure. I want ZRS. ZRS spreads it over 3. Then we have GRS. So with GRS, there's 3 locally, and then it asynchronously replicates it to the paired region, and then at the pair, I have 3 copies as well. So if you think about this picture for a second, so now there's a second region hundreds of miles away. Also with GRS, let's pick another color, I have those 3 copies within that one data center, but it's going to asynchronously replicate it to a data center over here, where it will now get stored 3 times as well. So that's GRS. And there is a variant, RA-GRS, that lets me actually read from the replica. So if you saw a question that was like, hey, I want to store my data in Azure Storage, I want to make sure it's available even if there is a region outage, well, it's going to be GRS or RA-GRS. GRS means it's geo-redundant. It's replicated to another region. Now, there is a combination of ZRS and GRS. So there is actually kind of a GZRS and then an RA variant. That just means it's ZRS stored in the primary, asynchronously replicated, with 3 copies there as well. So that's the GZRS variant. So that would give me resiliency from a data center failure within region, and then I still have resiliency from a region level outage. So understand these. Understand that replication is important to know the redundancy of my data. So that's about redundancy. And again, remember this survives a region level outage. We also have performance. And there's basically tiers of kind of hot, cool, archive. It's to do with how much it costs to store the data, how much it costs to actually do transactions, how readily available is it. So the old default was just hot. The data is always available. I pay a certain amount for storage, a certain amount for transactions. Then they introduced cool. So cool, it's still immediately available. I pay less for the storage, but I pay more for the transactions. The idea is I'm going to access it less frequently. And then there's actually, under this, we'll say there's archive. Now with archive, it is not immediately available. It's essentially offline. I'll still see it, but I can't read it straight away. It has to be moved back into cool or hot. Obviously, that's the cheapest. So the price goes down as I move down those various tiers. So if I saw a question that was like, hey, I want to store the data as cheaply as possible, I don't need immediate access. Archive. If I saw a question, I want to store my less access data, but it must be immediately available, well, that would be cool. If I saw a question, hey, what should I use to store my constantly accessed data to minimize transaction costs? Well, that's going to be hot. Now, at a kind of blob level, I can move them independently, but what you're probably going to want to do is there's actually something called lifecycle management. And here I can kind of create these rules. And what I can say is, hey, look, if something's not been accessed for 7 days, move it down. If something's not been accessed here for 30 days, move it to archive. So lifecycle management lets me automate the moving of the data between the tiers to really optimize my spend. And proper name might be storage lifecycle management. Make sure you guys check and look that up. but that will help me automate all of those things. So I have these rules, these policies that can automatically do that. And again, Azure Data Lake Storage Gen 2, because it sits on Blob, it can use this as well. So that's kind of a super cool capability. So that's our kind of basic Azure storage. We have all these different types. So Azure storage is phenomenally powerful. Don't instantly skip, oh, I wouldn't use an Azure storage account. It can do a lot of things, especially with now things like the Azure Data Lake Storage Gen 2 sitting on top of Blob. Blob is super cheap, kind of almost this near infinite set of scale. So don't kind of just overlook that thing. And there's another type of performance available as well. There's kind of like a premium around IOPS. Generally, I don't think that's going to be something you'll get questioned on, but if it's like, hey, we need a higher IOPS and is available with the standard tier, well, there's a premium that I can actually use as well. Okay, so let's talk about some other types of data. So that maybe as we get more advanced. And what you'll topically hear is things like OLTP and things like OLAP. So online transaction processing. This is what we commonly think of for regular kind of relational databases. We think kind of, in fact, just writing DB is not a great thing. They're both kind of databases. I'm actually going to move this down a second. Let's move this down over here. So I can think about high volume. So I've constantly got high volumes of probably small transactions. So they're small things, but they're constantly coming in. These are activities for application being stored as they're happening. I want very fast access for the querying when I'm doing operations against them. Commonly, I'm going to normalize the data. I'm breaking it down into different types of tables. Again, remove redundancy, duplication, make it very efficient for when I'm querying it. I think of atomic transactions. I have the ability to make sure, look, if I do this right, well, then it happens to all of them or none of them. I'm not going to have half of the transaction processed. They all succeed or none of them succeed. And these are what we think about things like SQL. So this is like SQL is a huge one around this. And then with OLAP, well, this is more like very large volumes of data in terms of size. I want to capture the raw data. We typically think about this like data warehousing type solutions. I'm going to run analytics against this to get insight into various things that are happening. And so traditionally we think of like a data warehouse here, and there's other types of solutions around this. But I want to kind of focus on this OLTP initially. So again, there's different types of service available for this. SQL Server is an obvious one. There is also kind of the Azure Database, where we have that Postgres, we have MySQL, and we have MariaDB. Again, these are the community editions. These are open source, but it's managed. It's deployed for me, it's patched for me, it's looked after, not doing the operating system. It's just provided. HA is inherent to it, as backups inherent to it. It's just there for me. Whereas this OLAP, this would be more like Synapse. Although Synapse is evolving, it's doing a lot more than just OLAP. But these are kind of the common things we'd actually be dealing with. So let's actually focus on SQL Server for a second. So if we go over here, to a bit of space. So SQL Server. Again, I can run this in different ways. I can do an IaaS version. So in an IaaS world, I could install SQL Server onto a VM. But then I'm patching SQL Server, I'm maintaining it, I'm doing all of those things, and I'm patching the operating system. In a PaaS world, kind of database as a service, this would be things like Azure SQL Database. Now, there are various types of that. There's sort of elastic pool where multiple can share a set of resources. There's hyperscale, there's serverless, there's different SKUs of it. But essentially, it's Azure SQL Database. They're typically the ones we can use. Managed instance actually deploys into a virtual network if we need those capabilities. But these are relational. And I'm going to really focus on this kind of PaaS world. So we have these relational databases. And so the key point about this then, if we're relational, we have the database and we create tables. So this table, remember, we define the columns that we have in here. So we have a strongly typed schema where we define these columns that we can have. They're the attributes we can have in there. We have a primary key that has to be unique for every record within that table. So we have the rows, these are the records, so we're going that away, and then we have the columns, the various attributes of the data. So that's core about the table and the schema. Now, I might have other tables. I have another table over here. Once again, it would have its own kind of primary key for its records. And it might be this column over here actually references this column. So this would be a foreign key. This might be some ID that I then go and look up. Again, normalization, we break the data into different tables. So this is now opens up to various types of architecture models for the schema. Because I can use these various relationships to foreign keys. And when I interact with the data, it doesn't matter that the data is in different tables. I can do various types of joins. I can view across them. Now, there are potential performance implications of it, but I can absolutely access this. I can create views, which I have this certain way I'm interacting with the data that's actually made up of maybe data from different places. So I can bring these things together. But this ability to have these kind of relationships, these foreign keys, open up to various types of database schema, these patterns that we'll actually commonly see. So the first model is what we call a star schema. So what we have in the middle is kind of the primary table about our data. And we call this kind of the fact table. So this is the main data. And then what we have all around it are these other tables. Kind of looks a bit like a star. And these have some aspect of detail about one of the various dimensions of the fact. So these are called dimension tables. So these are all called dimension tables over here because they have information on one dimension of the main fact table. So these would have foreign keys. So this foreign key might link to this. This foreign key might link to that one. This one to this one. So I can go and trawl outwards and get that information. So this is the star schema. Again, remember that because, well, it kind of looks like a star. I might normalize further. So maybe these tables, well, they have some other information about something else. So I might then have other tables out here that, well, this column references that. They have their own foreign keys to other things. It's kind of filtering out like a snowflake. So this is called a snowflake schema. And these are all dimension tables as well. So if you just see a pattern where it's kind of a central table and then things just it relates to, that's star. If it filters out even further, the dimension tables have relationships to other dimension tables, well then that's Snowflake. So kind of remember those two things. There is also another pattern where I can think once again, I have my facts table, and once again I have dimension tables, even quicker and quicker. So we have that again. So once again, these are dimension tables. So this is a star, essentially. Remember, this is the fact table. So we have those relationships going, whatever that is. But now I have another fact table. And that fact table, well, it uses those as well. And maybe it has some of its own ones over here. So essentially I have multiple stars. What's multiple stars? Well, that's a galaxy. So there's a galaxy schema as well. Again, the terminology, the one in the middle, the one with the core attribute, the dimensions that reference other things, that's the fact table in all of these models. The things that hold that additional info that I look up based on some ID in the fact tables, they're dimension tables. If it keeps going outwards, well then it's a snowflake. So they're the core models that we actually think about, that those foreign keys allow, those relationships allow. Now to actually integrate and do things with SQL, what do we use? Well, you've probably heard of T-SQL, Transact SQL. So this is how we actually do stuff. And what we actually have is, if I'm dealing with the data, now there were commands to create table, drop table. But if I actually want to manipulate data, there's actually the data manipulation language. So DML. So these are things that actually change the data. So that's the key point. Data manipulation is data change. Now, the focus on that word change. Sometimes this select statement is included. And that's more of a data query language, but sometimes you will see that creep in. But really, data change is around kind of insert. So I'm inserting a record, I'm updating a record, or I'm deleting a record. Obviously, if it was select as well, I'm going to kind of draw that in a little bit of a different color. With select, I can say, hey, select star or these particular columns from a certain table. And I can optionally do like a where. So where a certain column name equals John. Probably not John, but you get the idea. Select these attributes or star for all of them from this table where something equals something. So that's kind of the format. It's important to kind of understand the basics of the format of these commands. So go and look these up. So if I was doing insert, well, I'm inserting into a particular table name. And you may see DBO dot. DBO dot is just the default schema of the database, DBO. So I want to insert into the table bracket. Well, which columns am I inserting into? So I'm going to insert into column 1. You actually put the column name like first name. I want to insert into column 2, 3, etc. And what I'm going to insert into there are values. So I'm going to insert the values and then what the values are. John, 45, etc., etc. So the things that make that up are I'm inserting into, insert into a table, these particular columns, those attributes, and then the values I'm putting in there. So make sure you understand the basics of the structure of that data manipulation language. It's just important to understand those things. This is where indexes come in. So when I start doing where statements, think of an index of a book. Remember all those records? Remember way, way back. It's a long time ago now. but we kind of wrote about the types of data, and it writes out that way. So imagine I was doing a selection on age. Well, I'd have to go and read every single record to go and find age. So one of the things we can do, if there's a certain column that we constantly want to go and look up, or maybe perform some operation on constantly, we can add an index. So just like a book, now I can quickly jump in that index and it will find me the record ID, so I don't have to go and parse through every record. So it's going to speed up interactions. Remember, there's always a flip side. By adding an index, well, there's more I'm storing now. I have to store the index, but also now there's going to be a penalty to write. When I write data, it now has to go and update the index with the new entry. If I had lots of different indexes for a book, every time I added a page to the book, now I have to go and update every single index for whatever's in that new page. So indexes will speed up querying, things like that, but realize there's going to be a penalty in terms of where it has to store the index, and also there's going to be a performance penalty to actually get that when I perform writes or updates, so we can update the index. So it's important to be there, but realize that nothing is completely free. So they're the basic formats. That's relational. Then we have NoSQL. And what this is really saying is, well, it varies. Some people say it means it's not SQL. Some people will say it means not only SQL. I don't know if there's an absolutely right or wrong there. And really it's talking about relational. So it's not relational, it's not only relational. So we have different options about what we're going to do. And there are various solutions in Azure around sort of NoSQL. I'm going to focus on Cosmos DB. So Cosmos DB is kind of that managed offering in Azure. And one of the crazy things about this actually enables me to do multi-region write. With a relational database, it's a single primary. I can only write to one of them. For Azure SQL Database, for a lot of the offerings, the Azure Database, I can add additional replicas in other regions for resiliency, even performance. I can read from them, but I can't write to them. It's that single primary that's allowed to make changes, and it replicates outwards. So it's focused on consistency, making sure I have that data. With Cosmos DB, I can actually write to multiple copies. I can have a huge number of replicas of my data. And I can set this ability for multi-write at creation time or after. So I can modify it. Now you might, if you know databases, you'd say this is impossible. You can't do that. It's all about CAP theorem. The idea that I can kind of pick between partition tolerance, availability, consistency. And sure enough, you always have to give up something. So the point of Cosmos DB is I can have a variable consistency. And that really goes from strong consistency, which is what we'd see in a relational database, all the way to eventual. There's kind of these different markers in between. Sessions are kind of common one. Within a particular session, RC read and writes in the same order. But with eventual, I can now write to multiple copies and eventually they'll get in sync. Within my session, a session would go to a particular copy, RC read and writes in the same guaranteed order, but they get consistent over time because I can't generally synchronously replicate between regions. The performance would be terrible. I mean, that's what strong would do. Strong would say, hey, I'm not going to acknowledge this write until it's also written to all of the replicas. That's why I cannot do multi-region write and strong. I cannot have that combination. It wouldn't make any sense. Hey, I want to be able to write to multiple regions, but I require a strong consistency. I'll always see the same read and writes from any copy. But if it's strong, it has to write to all of them at the same time. So why would I bother having multi-region write? It wouldn't get me anything. So I can't do multi-region and a strong consistency. But I have a lot of flexibility in how I can do this. So I can, based on my workload, again, session is super common. Certain processes will share a session and they'll see the same order, read and writes. So I have that configuration. Also, when I stand this up, I can kind of do a prod versus non-prod. And this doesn't have any impact on performance or features. It's simply all about my portal experience. The things it shows me in the portal, we have different priorities based on if this is a production workload compared to if I'm doing development things. I want to see different things by default. So that's really all it's doing. Then we pick an API. This is what's crazy about Cosmos DB. It has 5 different kind of data models, different APIs that it can support. So it has kind of a SQL and a MongoDB API support. So when it's doing this, well, this is using document model. Remember document, for example, JSON, super common, but it will parse that data. I can still go and index and query based on that. Then it has Cassandra API. Cassandra API is that column-based storage. When we talked about that Columnar, this is that. That's not column. Column. It also has table. As you probably guessed, table is going to be key value. And then lastly, we have Gremlin. Gremlin is graph. This is set when I create the account. I can't have multiple within one. So I create the account, I pick the API. So I have all these different types of API and therefore the different types of data I actually want to use with that. And the way I do performance in this is something called request units. So request units, RUs, anything I do against Cosmos has a certain cost. A read against one partition is maybe cost me 1 RU. An update that has to go and look up some other things and go against multiple ones is maybe 5 RU. So there's a certain cost. And I can do those either as provisioned, I want 1,000 RUs, and it will actually throttle me to 1,000. So if for some reason I hadn't got enough and I was doing too much, I'll actually get errors back saying, hey, we've throttled you, you ran out of RUs. Or I can do auto scale. Auto scale, I can set a maximum number of RUs, but rather than always billing me for 1,000 if I'm using them or not, it will bill me for the number I'm using up to that limit, and then it will kind of cut me off. And I can really assign these. So we have various constructs in Cosmos DB, but we have a database, so I can assign them at the database level. And under databases, I have containers, or tables, or graphs. So I can kind of assign them at different levels under that. So I have these capabilities, Cosmos DB, again, super, super powerful. And like I say, I can set up replicas of my Cosmos DB in 30 different regions. Things like Azure SQL Database, maybe I can have 4 read-only replicas in different regions, and this, I can have it in nearly every region. And remember, the replicas are not just for resiliency DR. Hey, amount of instances in those regions, I want to be able to read from the data. So it's super powerful for that. Finally, before we get into actually getting data into the solution, obviously there is a data warehouse solution. Hey, I just have huge amounts of data. I want to run great analytics against it. This is Synapse. So Synapse was formerly SQL Data Warehouse. Now it's Synapse. It also not only has this huge storage, and it can use things like Azure Data Lake Storage Gen 2 for its storage, but it also is now bringing in things like Data Factory which I'm going to talk about, and things like Databricks, which I'll talk about as well. So really, the point of Synapse is trying to bring all these things together. It's my go-to analytics place. And one of the nice things they've done with Synapse is we talk about kind of compute and the storage. And I can kind of scale these and pay for them, but I can pause the compute. So I can actually essentially stop paying for that part of the service. Again, with SQL Server serverless, I can do that, but not with the other types of SQL. This actually lets me do that. So if I think about a data warehouse, hey, question, I want to do huge amounts of storage on this data. Where should we store this and then be able to perform analytics against it? It's going to be Synapse. I want a store service where I can pause the compute within my data warehouse, Synapse. And then we can kind of think finally just about tooling for these kind of SQL-based workloads. And there's two main ones we'll see. So there's the SQL Server Management Studio. So SSMS. This is the traditional. This is for kind of the real deep management. I can do things like look at the query store. I can manage things like HA. I can actually go and look at, well, generate me the SQL statements to do these things. Real deep, complex, deep administration. So probably not dear. That means that. Deep. So that kind of deep management, a deep admin. And there's a new one. We have this very nice Azure Data Studio. And also, while this is really Windows, this is kind of multi-platform. It's open source. So there's Windows, there's Linux, there's Mac OS. And this is more for kind of, hey, data queries. I want to maybe do visualizations. I can actually create queries and put them on a dashboard. There are extensions. So yes, I can use this with Azure SQL Database and Deep Data Warehouse and SQL Big Data. There's an extension for Postgres. So I can manage that through Azure Data Studio as well. So I have these two tools. Again, deep admin, I'm doing SQL Server Management Studio. It's not going anywhere. If I just want to do some sort of queries, some interactions, well, that's really Azure Data Studio. I guess what I'm talking about, tooling, obviously there's things like Power BI, desktop, etc. So if you see anything around visualization, and that's kind of the Power BI. So visualization, insight, that's what they do. So different tooling available. So this is, okay, all of this stuff, all of this, done a lot, I've done a lot so far. All of this is all about storing the data, which is great, and we definitely want to do that. But how do we actually get the data in? How do we get it in a useful format? So I can think about, hey, I've got the data. Let's go over here. I can think about batch processing. So a batch processing, the really data comes in and the data is collected. It's just stored somewhere. Maybe it goes to that Azure Data Lake Storage Gen 2. It's just written somewhere. And then it's processed on an interval. So maybe once an hour, once there's 500 records, there's some interval that it goes and takes it and processes it. So it's going to kind of process large volumes of data. And there's going to be, therefore, a latency, a delay, because it's not doing it real time. The nice thing about that is I can then throw massive amounts of processing at the batch to go and process it, these big MPP systems. The other option is stream. So with streaming, I can really think about it's processed as it arrives. So batch could be an example of reporting. Here I have all of these reports written to a folder, then I have to process them all and do something to it. Stream may be, hey, IoT devices constantly sending in these little bits of data. I have to process it as it arrives. So I can kind of think about this being almost real time or super low latency. But it means that I have to make sure I scale correctly. If I'm processing it in real time, I can't run out of resource. I can't process that incoming transaction because I'd lose it. And that would be a huge problem. So I think about data coming in. Hey, batch, I collect it up, I grab a bunch of it, process it. Then grab the next bunch maybe 10 minutes later. Streaming, hey, IoT, something constantly coming in, I'm going to process it as it arrives. Now often, the data coming in is not in the format we want. So there's multiple phases to this. We'll often hear this ETL. So we have to extract the data from something. We have to transform it into the right format, maybe clean it up. Maybe there's bad data, there's null records, there's dates in different formats. We have to clean the data, get it into a standard format, and then we'll load the data into something. So again, this ETL is super, super common. There's challenges with ETL though. It was really popular in the old days where storage was a problem. We had all this data coming in and we wanted to transform it, get it as small as possible so we could store it somewhere because storage cost a lot of money. It's not really the case anymore. And one of the downsides with this transformation before we load it, i.e. store it, is I may not know the question I want to ask tomorrow. There's maybe some aspect of the data coming in that I've removed by the transformation. I've lost it forever. So what's more common today is extract, load, and then transform. And then you can kind of think about once we've transformed it, we kind of go back and store it again somewhere else. Because now we're capturing it in the raw state, then we go transform it, and then we go and write it to a format we can actually use for analysis or whatever. But if tomorrow I'm like, oh, wait a minute, what about this? I want to ask this question. Well, now I can go back to that data because we saved it in the initial format and transform it again. There's definitely an M in transform, to a new set of data that I can run a different type of analysis against. Now the one benefit of ETL is obviously I can prune the data. Maybe there's data I shouldn't store, or I can prune it first. But really ELT is really becoming the standard because again, I've got the raw data. It's great if there's questions I don't even know I have yet. I can always go back and transform it in new ways. Now, when I think about this transformation, there are different types of transform, and there's many dimensions. Again, it might be cleaning the data, standardizing a format. It might be very simple. I might just be mapping things. Hey, this field goes to this field, maybe a little bit of string manipulation. Or it might be super complex. It might be deep analysis of that. So transformations can mean many different things. And when I get to the really complex type analysis, this is where you're talking about things like HD Insight, Databricks. Databricks is kind of a Apache Spark, essentially. HD Insight has lots of different things, Kafka, Spark. I can do different things with HD Insight. But they have the ability to go and perform that complex. If it was just mapping, and there's lots of things that can do this, even Data Factory can do this basic kind of mapping. I could write an Azure function. There's different ways to do that more simple type of thing. The other thing that's made kind of this load so attractive in the cloud now is because the cloud, the storage is so cheap. Because it's so cheap and it's kind of this infinite scale, why wouldn't I just store everything in the original format? Remember, Azure Data Lake Storage Gen 2 is a fantastic landing zone. Very, very common. The answer to this is ADLS Gen 2. I can use those lifecycle policies to put the older stuff in archive. But that's typically going to be where I'm initially going to put my data, and then I'll go and grab it with something else. I'll go and grab it with Databricks. I'll go and grab it with HD Insight. I'll do those transformations. I'll go and write it to Cosmos or MySQL or Synapse. Lots and lots of different options around that. So I can do different things with it. That does raise a question, right? So, okay, I'm extracting, I'm transforming or loading, transforming, loading, got all these different things. What is doing that ETL? There has to be some kind of orchestration. Something has to run the various activities for the ELT or ETL, whichever one we're actually doing. So the answer here is Azure Data Factory. So Azure Data Factory is an orchestration solution. That is its job. Its job is fundamentally to get the data from the source and get it out to the sink, i.e. where is it writing to? That is the job of it. And the way it does this is it has a pipeline. So we have pipelines, and a pipeline has various activities. Activity 1, activity 2, activity 3, whatever that might be. And again, there's sources that it's going to read from. It can have multiple sources, and I can have multiple sinks. Data Factory is not really doing much with the data. It calls activities, which could be a Databricks, it could be HD Insight. It could do basic data mapping. But fundamentally, it's the pipeline that's orchestrating that control plane. So if you think about what this is the control plane it's dealing with. That's its job. Now those pipelines, they can be triggered. So I have various triggers. That trigger could be a schedule. It could be manual. And the schedule could be a window. It could be a tumbling window. Hey, go and get this 20 minutes of data, then this 20 minutes of data. And it could be an event. I could use Event Hub. Something gets written to this Azure Data Lake. Call this pipeline. Oh, it goes and runs this Databrick, and then it goes and writes out to Cosmos DB or Synapse, whatever that might be. And again, it can do that basic data mapping, so it could actually do some of those things. But fundamentally, Data Factory is the orchestrator that's going to make these things happen. It's just pipelines, a set of activities. I can have various types of trigger that will make the pipeline run and go and do the job. So that's the point of Data Factory. So, I mean, the source, it could be a CRM system. Then it goes and writes to Azure Data Lake Storage Gen 2. Then it goes and triggers a Databrick. And maybe that goes and writes to Cosmos DB. Or it could be Azure Data Warehouse, there's different things. And then, well, maybe it goes off to Power BI for the actual analysis, actually getting all of the insights into that data. So this complete flow, giving me that. Nearly there. So that analysis part, just kind of finishing that thinking pattern. When I think about doing analysis, so fundamentally we do all of this mostly because we want insights in our data. The rest of it, we don't care that much about. It needs to be done, but the point of it is to get us to this point because I want to do analysis against the data. Well, what is that analysis? So there's descriptive. Descriptive is tell me kind of what happened. So if I think about, okay, I've got some graph. Descriptive would be showing me that. Show me what happened. I might have diagnostic analysis. Why it happened. What did we do that made that happen? We might have predictive. What's going to happen based on history. So that might be, hey, that chart or predictive would now be, well, it's probably going to go somewhere in there. That would be kind of a predictive analysis. We can also say a prescriptive. A prescriptive is kind of like, well, what should I do if I want this outcome? Hey, I want to get to this. What should I do? And then finally, I can think about cognitive. That's going to basically generate conclusions. And those conclusions are going to be based on existing knowledge. So it's got some knowledge. From that knowledge, I'm going to generate conclusions from it. And again, for all of these things, I can think about Power BI, all of these analysis things, all of these are going to end up kind of Power BI for that great visualization, for giving me the insights. So I have all these different types of analysis. It's going to feed into that. Okay. Wow. I did not think this was going to be an hour and a half long. I don't know whether to apologize or not. We covered a huge amount. This is not designed to be a complete training course at all. You need to go and look at the syllabus, study. Think of this as maybe like an exam cram. Maybe a few hours before the exam, go and look at this. It might remind you of some stuff, help you put a few things together, maybe watch it at the start, study, watch it again at the end. I really hope this was useful. This was a huge amount of work, sort of research and planning this out. So a kind of like, subscribe, comment and share is appreciated. It helps other people find it. There's no adverts. I don't make any money off this. This is really just to help. And again, the more people see it, the more it helps more people. So good luck. Don't panic. Relax. If you take it and you don't pass, you've learned things about what you're weak on. You go and study on those. You'll get it the next time. So good luck and take care.